This is the last in our series of video-based lessons for this class, and it's on the topic of nonlinear and non-smooth optimization models. This material is covered in the supplementary Chapter A of our textbook, with the PDF provided as a link in this module on Canvas. We are going to cover the basic versions of a number of different nonlinear models listed on this slide here. From product pricing to portfolio optimization, what all these models have in common is that some aspect of the model formulation involves nonlinear functions, such as quadratic, power, or exponential. In addition, the non-smooth problems involve one or more of the non-standard Excel functions, such as if, SUMIF, COUNTIF, VLOOKUP, index, etc., all of which disrupt the smoothness of the quadratic, power, and exponential functions. Finally, there are some specific models I will skip, such as the economic order quantity models, or EOQs, job scheduling models, both included in the textbook, but I will have a few examples of the traveling salesman or TSP problem, which is one of the more difficult nonlinear problems around. As was already mentioned, all of the models listed on the previous slide fall into the category of nonlinear programming problems. In these kinds of problems, either the objective and/or constraints are nonlinear functions of decision variables. Relationships that involve polynomials, power, or trigonometric functions are considered smooth and are handled with Excel's GRG nonlinear solver. GRG stands for Generalized Reduced Gradient, where the word gradient is a synonym for a derivative. Okay, in high dimensional spaces, i.e., in calculus-based math. The GRG method attempts to find the point in the feasible region, feasible solution set, where the gradient or slope of the objective function is 0, which means that we found a local minimum, like this one here on the slide, top right corner, or a maximum. This is why GRG method does not work well with objectives or constraints that include non-smooth functions such as min, max, ABS for absolute, VLOOKUP, and all the others I mentioned on the previous slide. Okay, for those functions, the abrupt nature of changes in the behavior, like right here, pang, this kink, in sort of middle part of the slide. Okay, the slope is not well defined, so the GRG method sort of breaks down. Excel's evolutionary solver is much better at avoiding these kinds of problems, but as we'll see with our TSP examples, it is also much slower coming up with an optimal solution. Finally, in both cases, with either smooth or non-smooth nonlinear relationships, the optimal solution that either GRG or evolutionary solver finds cannot be guaranteed to be a true global optimum. This is why using GRG multi-start option, if applicable, we attempt to search the feasible solution space from different starting points in an effort to avoid getting stuck in a local optima like this here, right? So if we start somewhere around here, we're probably going to get stuck in this local maximum because the gradient or the slope is going to be 0 here, and this, the process is going to stop. Whereas clearly there is a maximum, a global maximum here that is higher, right? So that's sort of one of the many difficulties associated with these nonlinear problems. Okay, so we begin our study of basic pricing models by emphasizing the critical importance product service pricing plays in today's economy. With increased competition, both domestics and from overseas, as well as availability of ever larger amounts of data, the degree of sophistication in determining the best price has increased tremendously. It is not just about beating the competition by looking through the window to see the gas prices across the street, but the ability to continuously adjust prices as the demand changes, and this is becoming more and more crucial in today's business environment. The internet has made pricing transparent and readily available for both customers, consumers, and businesses, and taking advantage of that information has become the norm. Just by looking at the dynamic pricing of hotel rooms and airline tickets gives you an appreciation for the degree of complexity these industries are facing when determining the optimal prices that are going to have the best chance of having a positive income or impact, I should say, on their bottom line, which is the income. We will start with a simple example listing the basic requirements for a single product pricing system, right? Described here on this slide, and then concentrate on providing a few simple but effective models for estimating the demand based on a given level of prices. The simplest pricing model attempts to find the price at which profit is maximized. The profit is simply the marginal profit per unit, itself a difference between the price per unit and the unit variable cost, times or multiplied by the demand. Fixed costs could be taken into account, but in the simplest of profit model formats, they will not have an impact on the optimal price selection. This is because the fixed costs are simply going to lower the entire profit curve by a constant amount without affecting the optimal price at which the profit is maximized. When discussing the price selection, it is important to understand the concept of price elasticity, which is a percent decrease in demand for every 1% increase in price. The products or services with high price elasticity are said to be elastic, in the sense that a small change in the price is accompanied by a relatively large change in demand. This is often the case for products where there is lots of alternatives, like basic consumer staples. On the other hand, if a product price changes by a sometimes significant amount and the demand does not change much as a result, the product is said to be inelastic. A typical example is the price of gasoline, a product for which there are no readily available substitutes. We will often use the power demand curve, described here towards the bottom of the slide, when a constant price elasticity B, or negative B as it were, is known. We will also use the linear demand line model if we believe the demand decreases at a constant rate, or perhaps a quadratic relationship that captures some of the price regions with faster or slower decrease in the demand as price goes up. So we will start with a linear demand line model, or demand model in general, the formula which is the demand is A minus B times P, right? Where the P, of course, is the price, and A, B are the intercept and the slope. If we are given the price elasticity for the demand, we can then increase the current price by 1% and translate the decrease in the demand based on the price elasticity at that point. When we don't know the price elasticity, as is often the case, we can then use 2 points in a price demand space, right? One here and one here, perhaps one in a high level of demand or low, high level of price, and the one the opposite, the other way around, to draw a straight line to them, right? Typically, the price demand space is inverted. Prices are horizontal and demand is on vertical. I could not find the graphic to that effect, right? So one of the 2 points may be the current price level, the other one is previously known price point and the associated demand. Then we will use the XY scatter as just shown and a trend line to come up with a straight line equation. It is also important to note that generally speaking, demand estimates are the best around the current prices with the known demand. The further one goes in either direction with significant price increases or decreases, the less reliable the model in estimating the potential demand. So, next we're going to switch to the hands-on portion of this first video and open the lect6 underscore pricing Excel file. I'm going to zoom in a little bit to the left side of the model, demand models tab. We're going to assume the price elasticity is 2. Okay, and the current price is $100 with a demand of 500 units. Okay, so first we increase the price by 1% because it's $100. This happens to be $101. We can just type it in, calculate it. Doesn't really matter. Because the price elasticity is 2, this tells us then that a corresponding drop in demand will be 2%, which translates into 10 units, right? 1% of 500 is 5, 2% is 10, so that's 490. Okay, then we add a trend line that was already added here, okay, through these 2 points, one in the top left corner, one in the bottom right corner of this already, prepared, obviously, chart, and then we'll get the resulting demand equation D equals 1500 minus 10 times P, or Y equals 1500 minus 10X. So the interpretation of that straight line is that for each dollar, not percent in this case, dollar increase in price, demand drops by 10 units. Okay, again, and clearly this interpretation is most likely to hold near the current price, right? So the current price is 100, right? So if I create an equation here of A plus B times X or times P, as it were the case, right? I'm going to get that $500, right? So the further the price increases, for example, $110 that I had originally here, right? I'm going to get a 400 units in demand, which is a significant drop for increase in $10 in price. And obviously, if I go crazy and go to the end of the spectrum, which is sort of indicated here on the right side to 150, I'm going to get a demand of 0, which is probably not true. The same holds, if you move in the other direction to 70, or for example, $50, right? We get the increases in demand that are not as high as it probably would have been. Okay, so again, the demand model, simple linear demand model, holds the best around the current price of 100. So that would roughly translate here, plus minus 10 or at most 20 bucks. Okay, so this might be switching back to the presentation, a good place to